Okay, so in this video, we're gonna go over the Pythagorean identity and then other identities that we can derive from it by simply dividing by the sine and the cosine, right? As a reminder, our Pythagorean identity covered in a previous section was this. All right, so it's an identity, so whenever you see cosine squared plus sine squared of theta, you can substitute 1 in place of it. And you can also do all this rearranging here. You can subtract cosine squared from both sides. So you can say, all right, this is also true. All right. Or you can, instead of the cosine, you can move over the sine, the sine square. All right, to get this. All right, so all of these, they're equivalent. Right, and you can substitute them in an equation, or if you're proving an identity, you can also you can make use of these identities, right? Either one, right? As direct substitutions. Now, we can derive other fundamental identities and call these fundamental because they all derive from the basic trig identity. Let's say that we take our trig identity here and we divide through by, let's say, cosine squared. Right, it's an equation, so you just divide every single term by cosine squared. Right, and then we see here this becomes 1. Now here we saw in a previous video, sine of theta over cosine of theta is tangent, and when they're both squared, well, that just means that tangent is also going to be squared. Okay, so think of it as sine theta over cosine theta. There's 2 of each, 2 factors because of the square, so it's just tangent squared theta. And the same over here, 1 over the cosine squared. We know 1 over cosine theta, a reciprocal identity. That's secant, and since it's squared, we have secant squared of theta. All right. Okay. And then similar to this up here, we can rearrange the in any form here. We could say, right, we can have 1 is equal to secant squared theta minus tangent squared theta. Or we could say tangent squared theta is equal to secant squared theta minus 1. All right. Okay, or any other kind of permutation that you want to divide or excuse me, not divide, you want to subtract from either side of the equation. Okay, so in a similar fashion, if we're able to divide by the cosine, we should be able to divide by the sine. And so we have this is our second identity here. Okay, so again, we'll start with the Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. And now in this case, we'll divide through by the sine squared of theta. Okay, and we see here again now we have cosine over sine. That's the cotangent, and both of these factors are squared. Plus 1. And then over here, 1 over sine squared is, well, 1 over sine is cosecant, and since it's squared, this just becomes cosecant squared of theta. Excuse me, and now we have our next fundamental identity. All right, and again, we can always subtract cotangent squared from both sides. It gives us a new identity, right? Or we can subtract 1 is equal to cosecant squared theta minus 1. Okay. Okay, so those are the fundamental identities. Now let's start with some examples of basic proving identities, right? Using um, definitions or theorems that we've gone over so far. Now let's start with one. So prove the following identity. Tangent of theta is equal to sine of theta secant theta. Okay, so one thing that I want to, some kind of guidelines here. So we are proving this identity, so we do not want to move, or we cannot, I'm not saying we don't want to, but we can't. The inappropriate way to do this would be to treat this like an equation, which even though we see the equal sign, we actually want to prove that this is true, right? So in order to do that, we got to make sure to always work on one side only. Okay, so do not treat like a regular equation. Okay, so here I don't want to divide by sine of theta, right? In fact, something that may help is just draw yourself a straight line, and notice here down the middle, a vertical line, and these are two separate quantities. We want to make sure one side looks like this side, right? And that will complete the proof. All right, now the way we do that is using, in this case, we have at our disposal reciprocal identities and the those fundamental identities we just covered. All right. A good place to start, especially for something like this, here I see one term, here we see two. Well, what if I just change this to sine, to the cosine, right? And again, here I just looking at it, right? Years of doing this, I could see right away, all right, that is probably a good strategy, right? As you work yourself through these, right, always start with the sign that looks the more complicated, right? If there's only one term here, but several terms here, in this case two, try to see if you can combine them into one. All right, another good strategy is if you see secants and cosecants and all that, maybe convert them to sines and cosines. So secant, using the reciprocal identity, is 1 over cosine. And again, now we have this fraction here, we can multiply. All right, and we'll sine of theta over cosine theta is tangent theta. All right, and now this completes the proof. Right, because we have both sides equal to each other. Again, notice I stuck to working on one side. All right, moving factors over on either side of the equation is incorrect. All right, we want to prove that it is in fact equal. So that's how we only stick to just one side. Okay, let's try one more. So again, directions are the same here. Prove the following identity. And here we'll have secant of theta over 1 minus tangent theta is equal to 1 over cosine theta minus sine theta. Okay. Okay. So here I'm gonna start over here on the left side here, mainly because there isn't much that I could see here that I can do. So one thing I know I can do here is I see cosines and sines here. So let me change all this to cosine and sine. All right. Okay. And now we see this here, and another thing, now we have a complex fraction, right? So one thing I can do is, well, let me eliminate the complex fraction, right? The common denominator is cosine, so let me multiply, again, mathematicians' favorite thing to do, multiply by 1, right? In this case, 1 comes in the form of cosine theta over cosine theta, right? So what that does here is, right, when I multiply here, we have cosine theta over cosine theta for the numerator, which is simply 1. And then here, don't forget, we have to distribute. So when I multiply here, we get cosine theta. And when I distribute here, the cosine reduces to 1 with the cosine down there, and we're simply left with sine of theta. Right? And here we go. Now this completes the proof, right? This side looks exactly the same as that side. All right, and that's how you go about proving these identities, right? In this case, we have at our disposal the reciprocal identities and the Pythagorean identities. Right, later we'll introduce more, more identities that we can have at our disposal. But for now, that is what we have to work with. All right. Okay, so now we're going to look at, we're going to go back to, not the unit circle, but we're going to go beyond the unit circle. All right. Okay. So as we saw here, we started all this stuff about sine and cosine with a unit circle. Okay. Unit circle, again, radius of 1. Okay. But what if we just had a circle that was not the unit circle? Okay. All right, and then let's call this bigger circle, let's just generalize it to R. All right, now the way we define the sine and the cosine, again, it was a way to to relate an angle theta to the point xy here, right? So the point P right? We defined it as cosine theta sine theta. And it was just a way to relate the point on the unit circle to the angle in standard position extended from the terminal, the standard position side. All right, now so here. Okay. All right. Now, if we extend this triangle here to the larger, and here we're going to use a little geometry. All right. So again, remember the larger triangle is a circle of radius r. All right, and there are also the smaller one and the larger one that are called similar triangles. right? In that they are going to have all the same angles, right? Theta, they have the right angle, and then this angle has to be the same, right? Because they add up to 180. Okay, and one thing we know about these similar triangles, right, while their sides, they're not the same. As we can see, one has longer sides than the other. What we do know is that the ratio of the sides are the same, right? So what I mean by that is, here, let's call this side S here for now. Right? I know the hypotenuse, right, since it's this is the equation. The hypotenuse of the bigger triangle is r, and of course of the smaller one is 1 because it's the unit circle, right? And then here, this height is cosine theta. So what I mean by it being in a ratio is if I take this side, cosine theta, over 1, the hypotenuse, it'll be in the similar ratio as the longer side here, which is s, and then the hypotenuse, which is r. Right, and here solving for r, here we get, or excuse me, solving for s, right? S by cross multiplying is equal to r times cosine theta. All right, so if I call this point Q, this now becomes r cosine theta. And in a similar way of setting up some similar triangles, the y-coordinate would be r sine theta. Okay. All right, so now we could see that in the larger circle, right, what we have here is that x is equal to r cosine theta, or in other words, cosine of theta is equal to x over r, and y is equal to r sine theta, or sine theta is equal to y over r. Right, where r is the radius of the circle. In this case, it is not unit, right? Notice that if it's a unit, r just becomes 1, and we get back the similar properties we've been working with previously. And what I can actually do is rewrite this as actually a function of, or actually I shouldn't say a function, as an equation in x and y, right? Because if r is x squared plus y squared is equal to r squared, solving for r by taking the square root, we get r is x squared plus y squared. Now I choose notice that if we take the square root of a square, we should always have plus or minus, but r is dealing with a length, so length is always positive, so r in this case is always going to be positive. So an alternate way to represent cosine theta is making that substitution for r. All right. And now we have a different representation of cosine theta sine theta that involves x and y. Okay. And we can extend this to using the reciprocal. So if we're dealing with the secant of theta, just take the reciprocal. And same for the cosecant. Right, and I guess the tangent, there's not much change here. Tangent of theta is y over x. Right. Okay, and notice here that it's still cosine over sine, because if we use the r formulation, the r over the factor of r simplifies to 1. So there's not much change there. The cotangent of theta is still x over y. Okay. All right. Excuse me. Okay, so now we can use, let's do some examples here using values that go beyond the unit circle. Okay, so in this example, let's say we say suppose the terminal side of theta when plotted in standard position contains the point -4, 3. Okay. Find the values of the 6 circular functions. All right, so let's first just start off to just a quick sketch of the point here. 1, 2, 3, 4. 1, 2, 3. So -4, 3. Okay. So again, not in the unit circle. All right, but that's okay, right? We can extend these formulations here as we've seen to to points that are outside the unit circle, right? That lie on a circle of radius r, right? And our theta in standard position, so this is theta. Okay, and we saw here cosine of theta is equal to x, which is negative, well, let me just write the equation so we can recall what we're using here. X is -4. -4 squared plus 3 squared. And we have -4. 16 plus 9 is root 25. And let's reduce that, or simplify it, to the form -4/5. All right. So this saves the work for the secant of theta. That's equal to 5/4. All right. And for the sine of theta, right, and we did most of the work here, right? The denominator is going to stay the same. The only difference here is that 5. All right, excuse me, the 3 in the numerator is the only difference there. Okay, and now right away we get the cosecant. That's 5/3, and we also have tangent theta. So that is x over y. Excuse me, y over x. So -3/4, and then cotangent theta is -4/3. Okay. All right, and we see once we did that first calculation, the rest was just substituting in the values for x and y. Right, we just need to find r essentially. All right, let's try one more example here. Okay. So we say suppose theta is a quadrant 4 angle with the tangent of theta equal to negative 1/4. Right, find all values of the 5 remaining circular functions. Okay, so quadrant 4 angle, so the angle in standard position is somewhere here. Okay, so keep that in mind, right? This information was given, it's an important piece of information there. So let's make sure that we use that. All right. And if we treat this as x and y, then r is going to be the square root of negative 1 squared plus 4 squared. So this becomes root 17. All right. So cosine of theta. Okay, now here be careful here, right? Negative, even though we see that it's written here with the 1, that doesn't necessarily mean that it's the x coordinate that gets the negative, right? That's where I make use of this quadrant 4, right? Quadrant 4 is here, so in this quadrant, x is positive, y is negative, right? So this is a very vital piece of information to let us know that in this case, the cosine will be 4 over root 17, right? The x, right? Y over x. All right, and then for sine theta, we get negative 1 over root 17. Okay, and secant theta, reciprocal identity, root 17 over 4. And cosecant theta, negative root 17, right? Over 1, but again, we can just write it as negative square root of 17. And the last one we're missing is the cotangent. Using the reciprocal identity, we just get negative 4. All right. Okay, so by now, working with these right triangles, we've probably seen that, okay, well, if we think of the acute right triangle, theta, where theta is an acute angle, right, we can define this side, and again, this is all in reference to theta, right? This side is adjacent to theta. This side is opposite of theta. And then lastly, we have the hypotenuse. All right. And we could see from all the work we've been doing with the sine and the cosine, another way to think of the cosine of theta, right, is the adjacent over the hypotenuse. Right? And another way to think of the sine of theta is to be the opposite over the hypotenuse. And the tangent of theta is opposite over adjacent. All right, and of course the reciprocals from there are just the reciprocals of these values. All right, but another kind of nice way to remember this, right? Cosine adjacent over hypotenuse, sine opposite over hypotenuse, and tangent of theta opposite over adjacent. Okay, so thank you.